Good evening, everyone. Welcome back to our problem solving session. Today will be the last problem solving session for this entire course, and this is basically a summary session for the NPTEL course Control Engineering, where I'll be discussing or summarizing. I should be precise. I will be summarizing what all we have discussed in this entire 12-week problem solving sessions. So yeah, I am Teja Golla, a fifth-year research scholar working under Professor Satanu Kapat at Embedded Power Management Lab, IIT Kharagpur. So let me share my screen. Kindly let me know when you can see my screen. Can you see my screen?
Yes, sir.
Okay. Yeah. So basically, this, as you know, this course is uh, of control engineering, and we have 12 weeks. And I have listed down the titles of the week. So in week one, we have discussed about the mathematical modeling of systems, basic type of system, what type of systems we have seen. And in week two, we have learned about Laplace transform, how to get the transfer function as well as block diagram representation. And then we have discussed about block diagram reduction and time domain representation as well as Mason gain formula. In week four, we have discussed about the stability, especially Routh-Hurwitz stability criteria, and we have solved many numerous problems to understand how to get the stability of a given system, also auxiliary equation, all these things. And then in week five, we have discussed about root locus thoroughly. And week six, we have discussed about the frequency response, especially the Nyquist and Bode plots. In week seven, we have discussed the basics of controller design. Then we have moved to design using root locus, design using Bode plots. Then we have also discussed about the minimum and non-minimum phase systems. Then in week 11, we have discussed about state space analysis. And week 12, we have discussed about the design using state space. So I'll just briefly go through my notes. Uh, so I'll be doing in this way. I'll summarize what we have discussed in week one. Then I'll ask if you have any questions. Then week two, week three, week four. So it is not in detail. I would browse so that you can brush up what all topics we have covered. And if you are feeling any, not so comfortable with any topic, you can let me know. Maybe I can give some inputs, or I'll tell you which lecture you have to go through. So this is not teaching. Instead, we'll just summarize what we have discussed, and then we'll just see all the concepts that we have discussed in this 24-hour problem solving session. So yeah, in week one, it was about mathematical modeling, and we have started with system. What is a system? We have basically defined the nomenclature, like what is input, what is output, and then representations for time, input, output, delay, as well as disturbance. Then we have classified the systems because we need to also identify which system is given to us. So whether it is linear or non-linear, that we can do using superposition theorem, and we have explained that. And then we have also discussed what is static system which doesn't have any memory like resistor. Then we have also discussed about a dynamic system which has memory like capacitor as well as inductor. And then we have seen the time domain relation between voltage and current of resistor, inductor as well as capacitor. Then we have discussed about time variant as well as time invariant systems. So what is time varying, what is time invariant? We have given standard examples. And then we have discussed about causal system as well as non-causal system and how to identify such systems. Then we have solved a couple of problems which are linear, non-linear, causal, non-causal, time variant, time invariant. All sorts of examples are touched. So we'll identify which is linear, which is not, and which is causal, which is not, and which is time variant and which is not. So I will not be discussing the problems in detail since this is already discussed it. I'll just briefly explain what these problems are supposed to target, which concept, and what we have actually discussed in the problem. Yeah. And one important thing is any straight line that is passing through origin is linear. Any straight line that is not passing through is non-linear, because the the immediate thought process would be a straight line is linear, right? But a straight line is linear if it passes through origin. If y equal to mx plus c and c is not equal to 0, it is non-linear. Why? Because it doesn't satisfy superposition theorem. So straight line doesn't mean it is linear. So that is a very tricky thing because it seems like it is linear, but it is not. Yeah. Then we have discussed about the control system. What does a control system has? Basic controller as well as system. In the future, we have discussed more detail like feedback, sensing, disturbance, etc. Then we have discussed multiple systems and the mathematical model, starting with the series RLC, second order system with input voltage. Then we have discussed about a mechanical system, which is again a mass spring damper system, which is also a second order. Similarly, we can get rotational motion equation as well. Then we have correlated between the mass spring damper as well as the RLC, because this is a second order, that is a second order. We can individually compare, and we have compared which parameter is corresponding to what parameter. And this is the another problem where mass spring damper is given and we are asked to write the equation. So in first week it is more about mathematical modeling, and we have also discussed about the predator prey model, which is very interesting, and what are the equations, and what happens if we give some initial condition and see how the population is going on. So it goes in a circle called limit cycle oscillation, and we have seen this in MATLAB also, which is a very interesting example. So if you have missed this, I would request you to go through week one lecture and then understand what I'm talking about. So any doubts till week one?
No, sir.
Okay. So in week two, we have discussed about Laplace transform. So the very first question we asked ourselves is why Laplace transform is needed. Because in time domain, it can become very difficult if there are complex expressions, especially in linear differential equations. So if we go to frequency domain, which means S domain, it will be easier to solve because everything will become algebraic sum, and then it will be easier to calculate. And also to find a solution, we can get the overall solution in S domain, and then we can convert back to time domain, because dealing with the integration as well as differentiation for exponential terms as well as trigonometric terms will become quite cumbersome, because you need to do integration by parts and do it multiple times. Whereas if you solve in S domain, it will be very simpler. So that's why S domain is used. And also for controller designing, S domain is much simpler than designing using time domain. Yeah, so we have defined what is the Laplace transform and what is region of convergence. And then we have seen multiple properties of Laplace transform. And again, I'm mentioning these are very, very critical. Not only you should know what are the properties, but also you should know when to apply which property. So it is very critical. And in this lecture or in this week, we have thoroughly discussed all the properties of Laplace transform, proved majority of them, and then also solved few problems. And I have asked students which property we can use. And we can use any of the property, but I have asked them to check their thought process, what they're thinking, how they're thinking, so that I have also given some input so that they'll know, okay, in this way I can think, and in this way I can proceed further. So if you use the property, it will become very simple, and you need not solve the actual inverse Laplace transform or Laplace transform. Whereas if you do not see the property and solve it by yourself, things can get complicated. So I will not discuss each and every property, but I'll name the property that we have discussed. So one is the time scaling property. And then I have also given a list of standard Laplace transform that you should remember rather than deriving it every time, because this should be handy and it will save time in solving the problems. So yeah, what I have done is I have given a property, and using that property, we have solved few problems. So one is time scaling, one is time shifting, and we have solved one problem on that, so that you will know how we are going to apply. So for each of the property, we have solved one or two problems. Then one is time differentiation, where if there is differentiation in time, how it will be reflected on the Laplace. Then we have discussed the time integration. Similarly, we have discussed the frequency shifting, time shifting, as well as frequency shifting. We have discussed time differentiation, and time integration we have discussed. Now frequency integration as well as frequency differentiation. So these are some of the rules, and important rules are the initial value theorem as well as final value theorem. And this will be applicable only if the limits exist. If they do not exist, then it is not valid. So we have solved two problems in finding the initial value using initial value theorem as well as the final value theorem. Then I have given certain problems. So in this question, I have not mentioned which property we should use, but I have told which property I'm using, so that looking at it, because there is exponential term, there is sine term. So we have to add one by one individually. So I have started with time scaling, then frequency shifting. In the other problem, it is frequency differentiation, again frequency differentiation, then time shifting, then time scaling, frequency differentiation, and frequency shifting. So if you solve more number of problems, you will be able to immediately get the idea of which property we are going to use. And if you see, I have not even applied Laplace transform. I have used the existing result to solve the problem. So in this way, it will save a lot of time. If I start solving the Laplace transform for this, it will become cumbersome. It's not that I will not be able to solve, but things will get really complicated. Then we have also done the inverse Laplace transform, where we will be using the partial fractions and then apply the inverse Laplace transform. So here also we might have to use the same properties, but for the inverse Laplace transform. And for some problems, it would be easier to use the property rather than solving the inverse Laplace transform. And then we have also discussed one important topic called convolution. So time in time domain, if it is convolution, in S domain it will be multiplication. If in S domain it is convolution, in time domain it will be multiplication. So this is a duality rule. And we have also seen find the convolution of this. So instead of finding the time convolution, what we do is we calculate the product of the Laplace transform and then apply inverse. So this is one way to find the convolution using the Laplace transform. So we, instead of directly doing the convolution, which requires integration, we convert them into S domain, multiply them, then apply inverse Laplace transform. So it might seem like three steps, but it will still be simpler than the one step using the integration. Then we have also seen what are transfer functions, how to define the transfer functions. We have defined for the RLC circuit, and we have gotten the RLC circuit transfer function. And then we have also defined what is a block diagram with the forward transfer function and feedback transfer function. And then we have also solved one ordinary differential equation using the Laplace transform. Had it been solved in time domain, it may be a little bit difficult, but here we have solved one such problem. Yeah. So any doubts till week two?
No, sir.
Okay. So in week three, we have discussed about the signal flow graph, block diagram reduction, as well as Mason's gain formula. So first we have understood the nomenclature. What is node? What is branch? What is input node? What is output node? What is path? What is forward path? What is loop? What is non-touching loops? And the nomenclature is very, very important. If you have any question, any confusion, I would request you to or suggest you to go through the video and understand them very clearly, because the formula is dependent on this nomenclature. So if you are confused about this, you will end up getting wrong results. So this is the Mason gain formula, how to apply this. So we have to first find the forward paths, then path gain of each forward path, and then we have to calculate the determinant. Determinant is given by this. And then we have solved one problem and applied the Mason's gain formula. So first you have to identify the forward path and as well as the loop and non-touching loops. Then we'll slowly apply one by one of this formula and then get the oral transfer function. And this is another such a simple problem where we have applied the Mason's gain formula and we have obtained this. So here I have given one block diagram. So the question is to reduce it using block diagram reduction and then Mason's gain formula. So if the block diagram is given, it is not always the easiest way to solve using block diagram reduction. Say if there are so many crisscross connections, then using block diagram reduction itself may not be so easy and straightforward to simplify the block diagram. But in some cases, it may be easy. In this question, it was a little bit straightforward because all of them can be solved simpler. So that's why we have solved using block diagram reduction, but not every problem can be solved. Okay, we have done it and we got the overall transfer function. And now for solving it using Mason's gain formula, first you have to draw the signal flow graph, which is very critical. Again, here you should not make any mistake. Once you do this, then forward paths, loops, non-touching loops, and applying the same formula, you will get the overall transfer function. And then signal flow graph, it is not always given for a given block diagram. Sometimes it can be equally applicable to electrical system, mechanical system. So in that case, we ourselves have to identify the nodes and then draw the signal flow graph. And once we draw the signal flow graph, then you can get it. Or what you can do is you can solve for this and then get the transfer functions. And then from there, you can draw the signal flow graph. So either way, you can solve the problem. And then we have also done the time domain analysis for the first order system. So if the input is impulse, what will be the output? What will be the steady state? If the input is unit step, what will be the output? Similarly, for an RC circuit, if a step input is given, what will be the output? So we have solved in the S domain and then converted back to time domain. And then same thing applies for second order system. But in second order system, you will have multiple damping. Based on the damping, there are four categories: underdamped, overdamped, critically damped, and undamped. So it is dependent on something called eta, which is the damping ratio. Omega n is the natural frequency, omega d is the damping frequency. And we have seen how the step response will look like. And we have also showed the same in the MATLAB as well. And then we have defined standard terms like TR, TP, MP, and TS. And then we have solved a couple of problems understanding all this terminology and how to use this formula to get these results. And then I have also shown the MATLAB to show the damping. So all the MATLAB files are also uploaded in the drive. You can always go through it. Then we have discussed about the steady state error. how we calculate the steady state error if it is step input, ramp input, parabolic input, and then what are position error constant, velocity error constant, acceleration error constant. And then also we have solved one problem based on that. And yeah, if you have any confusion regarding any concept, kindly go through that week. Yeah, so week 4 was about stability. Until here, any doubts?
No, sir.
Okay. So in week 4, we have discussed about stability. So we have started with simple pendulum to understand what is stability, which is stable system, which is marginally stable system, which is unstable system. And then we have defined something called Bibo stability and in frequency domain, which is stable, which is unstable. So green color is stable, red color is unstable. This gray color is marginally stable. And then how do we use Routh-Hurwitz criterion to get the stability or to assess the stability of the system? So what is the necessary condition? The polynomial should have all coefficients and all coefficients should be positive. If they do not meet the necessary condition, it means there are some poles on the RHP side and you need not even draw the Routh-Hurwitz table. Directly you can say that it is not satisfying the necessary condition, so it is not stable. Whereas if it satisfies, then you have to draw the Routh-Hurwitz criterion and see for the sign changes in the first column. So we have started with a simple problem where we didn't see any sign changes, which means the system is stable. And in the second problem, we have seen that it is becoming zero. So the first element is becoming zero is one case, entire row becoming zero is another case. So we have come across the first element becoming zero. So we will replace zero by epsilon, which is a positive number. And using the epsilon, we will solve for the entire column. Then epsilon will consider very small number, say 0.001, and then see if there is any sign change. If there is a sign change, then it is unstable, else it is stable. So epsilon can be considered 10 to the power minus 3, 10 to the power minus 4, just to get an idea whether the sign is positive or not, nothing else. So 0 will be replaced by epsilon if it's the first element of the row. But if it is entire row, then it's a different thing that is called auxiliary polynomial, and we have also solved one problem in to address that. So in this problem, again, there is a sign change. So the system is unstable. And then point number 4, here we have seen that it is becoming, entire row is becoming zero. So initially it was becoming zero. So I have written 0 0 0 and then differentiated the auxiliary polynomial. So that's why here you can't see any 0 because I have erased it and updated the Routh-Hurwitz criterion. But if you clearly see, this row will become 0. So if this row, entire row has become 0, not the first element. So in such case, the line above that is called auxiliary polynomial, and that itself is a factor of the given polynomial. So now we have to differentiate this auxiliary polynomial to get the elements in the this line where initially we got all zeros, and then now we'll follow the same thing and then proceed further. So now auxiliary polynomial itself is a factor of the given polynomial. So from this we can get the roots. So if there are no sign changes, then it means there are no RHP zeros, but we have to check for the polynomial. But this auxiliary polynomial has roots on the imaginary axis, so it is basically marginally stable. And auxiliary polynomial coefficients are real, so it will be always symmetric. So it can have two on the real axis, two on the imaginary axis, or complex conjugates, some on the left hand plane, some on the right hand plane. And then we have solved another problem where they have asked the range of k for which it is stable, marginally stable, unstable. Draw the Routh-Hurwitz criterion and see which is stable, unstable, and marginally stable. And none of them should intersect. So this is stable region, this is unstable region, this is marginally stable. So there should not be any intersection because stability is separate and instability is separate, marginal stability is on the border. So k can't have two values, or k can't have the same value which will result in stability as well as instability. So for unique k value, it is either stable or marginally stable or unstable. In this problem, the k is not coefficient, but k is somewhere else. And then here also we have seen how to get the criteria for stability, instability, and marginal stability. And here we have not given the characteristic equation, but instead we are asked to calculate the, or get the characteristic equation and then solve for the stability. Sometimes no such value of k exists. Means here it is not satisfying the necessary condition. So it is always having a pole on the RHP side. So for no any value of k, it is still unstable. So we can't stabilize with certain k. And here we have introduced ks. In this problem, it was k. and will not be able to stabilize it. Now we have taken case and it could stabilize for k greater than 2. And then we have also discussed about sensitivity and we have solved a few problems on sensitivity. Sensitivity is basically parameter, how the loop transfer function or the closed loop transfer function change with respect to a change in a certain parameter. And we have solved another such problem. And for sensitivity, it is the concept. You have to understand this expression and then calculate individually rather than remembering the final result. So you have to understand the definition and then do it accordingly. So any doubts till week 4?
No, sir.
Okay. In week 5, we have discussed about root locus. And root locus is also like one interesting topic because it is more of graphical method, and you can see how the poles are moving, how the poles hit each other and move towards zero, the angle of departure, angle of arrival, and this is also very interesting. But you should again follow the steps that we have discussed or sir professor has discussed. So first of all, we have discussed for negative feedback, although the root locus is applicable for positive feedback, but some of the rules are a little bit different. Since that is not covered in the class, I have not covered in the session. And as far as this course, only negative feedback systems will be asked for root locus. So initially we have discussed the gain criteria, phase criteria. Then we have started with the root locus rules. So 1, 2, 3 rules are root locus is symmetric about the real axis. So number of branches is equal to number of poles. And all the branches of the root locus start with the pole and end with the zero. So if a given system has few zeros, but more poles, it means there are zeros at infinite. So the pole will move towards the infinite, and the number of branches terminating at infinite is number of poles minus number of zeros. Any point on the real axis lies on the root locus if the sum of the poles and zeros to the right hand side of the point is odd number. So this will actually pass the angle criteria as well as the gain criteria. So that's why the root locus exists if the poles and zeros on to the right hand side of that point is odd number. So we have started with one simple problem which needs only these three rules, and we have obtained the root locus. Then we have slowly increased the rules, and then we have solved some problems which needs more rules. So first problem needed only three rules, second problem will need 1 to 5, and slowly we have added each rule, and then the difficulty in the root locus also has slightly increased. So the rule 4 and 5 is about centroid. Branches that are terminating at infinite will move along the asymptotes, and the angle of asymptotes will be given by this. But what will be the junction of the asymptote? That is called centroid, and centroid is given by summation of poles minus summation of zeros by number of poles minus number of zeros. Then we have solved this problem which needed all the 5 points to understand or draw the root locus. Then we have discussed about the rule 6, which is the break in or breakaway point. For that you have to differentiate dk with respect to ds and then solve for s. So all these s points will result in break in or breakaway point. So here we needed 6 rules, not 5. So slowly we have added one problem to understand the additional rule. So for solving, we have to do dk by ds equals to 0, and then you will get s. So not every point has to be a break in or breakaway. Only some of them may be break in or breakaway. So that depends upon where this point is lying. So I got s equal to minus 5.15, minus 2.84. That doesn't mean both are break in away points, right? Here I can see only minus 2.5, 2.84 is the valid solution. The other one is not, because their root locus doesn't exist. So it's also important to see which point is corresponding to break in or breakaway. Not every solution has to be break in or breakaway point. Then the rule number 7 is angle of departure slash angle of arrival. And here we have seen how to calculate the angle using the angle criteria. And then we have solved one problem where we have to calculate the angle of departure or angle of arrival. So we know that this point is the closed loop pole. So it has to satisfy the angle criteria, which means summation of all the angles should be what? Odd multiples of 180 degrees plus or minus. So in that way, we'll say at what angle it is moving. In that way, we can get the angle of departure. Since it is symmetric, if I know this angle, I will be also able to know this angle because it is like a mirror image. And then root locus 8 and 9 is the intersection point of the root locus on the imaginary axis can be obtained using Routh-Hurwitz criterion because that is marginally stable. So at certain gain k, if it is about to cross the imaginary axis, it is becoming unstable. So the same can be obtained using Routh-Hurwitz criterion, and this k is given by this expression. So we have solved one problem based on this now, which needed all 9 rules. So we have to draw the root locus and find the gain at which root locus intersects the imaginary axis. So we have used all the rules and then obtained the gain k at which it is crossing. For that we have done Raut-Hurwitz criteria. Similarly, we have solved another problem which has poles on the RHP side and how it is coming back. Sorry, zeros, RHP zeros. So at some point of time, they are crossing the imaginary axis. Again, we can find using the Raut-Hurwitz criterion, and I got the gain. And if I get the gain, I can also get what is the value of S, right? Because if I substitute this, I can solve for this expression and I can get it. And another similar problem we have solved. So we have solved different problems with different difficulties. If you see here, it is a little bit more difficult. So with the increasing order and the pole location as well as zero location, it can become a little bit complicated. Yeah. So that is all about week 5, which was about root locus, and week 6 is about frequency response. So any doubts till week 5? Okay, I guess no. And then week 6 was about frequency response. As we already know the advantage of frequency response over time domain response, because it is easy to study higher order systems because everything will become algebraic rather than integration differentiation. So we have seen how to get the steady state expression magnitude as well as phase. Then we have started with the polar plot, how to draw the polar plot. Again, I'll not go into the details of how to draw the polar plot. I'll just tell what we have discussed. So we have solved one problem and we have asked to draw the polar plot magnitude as well as phase as omega is starting from 0 to infinite. And then we have started learning about the Nyquist stability criterion and what is Nyquist contour, what is the condition that has to satisfy. So the expression is n equal to p minus z, where n is the number of encirclements of -1 in counterclockwise direction, where p is the open loop RHP poles and z is the RHP zeros of 1 plus g of s h of s. So Nyquist criteria will correlate the open loop RHP poles with the closed loop RHP poles. So the RHP zeros of 1 plus g of s h of s is nothing but the RHP poles of g of s by 1 plus g of s h of s. So in this way we have solved. We have started with a simple problem. So if it is encircling any point on the imaginary axis, you have to consider a contour around that point, not through that point, because that will result in infinite. And then we have moved from 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and then we have seen how it is moving. So we have done region by region basis, so we'll understand the Nyquist plot. And then we have again increased the order of the system and saw how things are moving. So the difficulty in the Nyquist will slightly increase. We have solved two problems based on the two totally understand. But one issue with the Nyquist plot is it is not so straightforward. If I have, say here it is third order, what if I have sixth order? It will become very difficult to understand because we have to calculate each and every value. It is not so straightforward. What if it goes positive and negative multiple times? How to find the intersecting point? So it becomes very difficult. In that case, Bode plot is much simpler because it is very easy. And we have started with the standard transfer function s 1 by s 1 by s plus single pole single zero, double pole double zero, conjugate poles conjugate zeros, and we have seen the magnitude as well as the phase plot. And then we have started with one such example. So what we have to do is, if there is product in the transfer function domain, then it will be algebraic sum in the Bode plot. So individually you have to draw the Bode plot and then combine all of them. So we have done the magnitude plot. Similarly, we can do the phase plot. So probably that I was in a hurry, so I have not spent much time on this. But what you have to do is individually draw the Bode plot of each, both magnitude as well as phase, and then add them. So that is how you should do. And yeah, that's all about week 6. If you have any questions, you can ask. Else, I'll discuss about week 7. And week 7 is basics of control design. So any questions till now?
No, sir.
Okay, okay. So in week 7, we have discussed basics of the control design, but we have first
No,
started with, sorry, were you saying something? Okay. So we have started what will be the effect of adding pole and zero to the closed loop transfer function, because we wanted to see what is the effect. So we have started adding poles. First we have understood theoretically, then we have seen the dominant pole concept. I think someone has messaged in the Okay, no doubt. Okay. So then we have seen what is the dominant pole concept. Dominant pole will have impact on the transient response. Any pole or zero that is far away from the imaginary axis will have negligible impact. So that we have seen using a couple of problems. So here we have added uh, to the open loop transfer function uh, more poles, and we have seen how the root locus is changing, and we have also seen the transient response. I've showed the MATLAB code for the same, and codes are again uploaded to the drive. Then we have seen how to design P control, PD control, PID control, and they have given certain requirements. To meet that requirements, we have to design the control and then see the stability or whatever they are asking condition whether it can be stabilized or not. So in this way we have solved using KP, KI, KD, and sometimes if you see in this problem P, it is marginally stable, and PD control, it can be stabilized but non-zero steady state error. PID controller, I can stabilize and have zero steady state error. So if the objective is to have a stable system with zero steady state error, P control or PD control is not sufficient. Instead we should go for a PID controller. Then we have understood what is lag compensation, which is similar to PI, not exactly PI, because PI will have pole at zero origin, I should say pole at origin, but here we have non-zero pole lag compensation, and we have learned what is the lag compensation Bode plot and what impact does it have. It will give phase minima, so that's why it is delaying the phase. And we have also discussed about the lead compensation, which is PD control, but not exactly PD control. Yeah, and we have seen where it is needed it will provide phase boost. So yeah, so this is all. In this week we have not actually designed the controller, but we have understood what is lag compensation, what is lead compensation, but not in detail of designing. So that was about week 7, where we have discussed why controller is needed, how we can stabilize by considering few problems, showing that P controller cannot stabilize, PD controller can stabilize, but zero steady state error is not possible, whereas PID controller can stabilize the system and can achieve the zero steady state error. So in this way, we have understood the importance of the control and also saw the impact of the zeros as well as poles on the open loop as well as closed loop transfer function. And in week 8, we have started discussing the design. Yeah. So week 8, if I remember the table, design using the root locus. So we have started with the root locus. So how we are going to add the lead and lag compensation so that the root locus passes through the desired pole locations, because root locus passes through the closed loop poles. So now we have to add the compensation so that the root locus, we are shaping the root locus so that it will pass through uh, the desired poles or the dominant poles. Yeah. So any questions till week 7?
No, sir.
Okay. So in week 8, we have again started just a brief summary about lead and lag compensation. Lead means it is derivative, so it will improve the transient response. Lag means it is having an integral effect, so it will improve the steady state error. So in a question, if they ask to design a controller to achieve some transient requirements, use lead compensation. But if it is given to discuss regarding the steady state error, then it is lag compensation. So this is the lead compensation, and this is the lag compensation generic, and lead lag compensation will have summation or product of both. And this is one problem someone has asked, so that's why I have mentioned here, but it is not related to this week. Then we have started design using root locus for lead compensation. So why it is lead compensation is the gain is insufficient, then we have to, what are the step by step. So we have given a step by step guidelines, and we are following the same steps to design the controller. So I have given one problem, and they have given the transient requirements. So the transient requirements I have to convert back to the pole location. So now I have to pass through this pole location, and I have to see whether a simple gain is sufficient. So I have to plot the root locus and see whether gain k is sufficient. If it is not sufficient, then I have to follow these guidelines theta from the pole location, how much additional phase is needed, etc., etc., and then I have to calculate this and then get the lead compensation. So these formula are there. I'm not going to discuss in detail because they are thoroughly discussed in that week. And then in that way, we'll get the gain k, the as well as the pole as well as the zero. So in that way, we have solved that problem for the lead compensation. Whereas when it comes to lag compensation, we are adding the integrator effect to get the zero steady state error. So these are the step-by-step guidelines, and we have solved one problem where they have said design specification. One is the transient requirement, and the other one is the error requirement. So we will see whether the transient requirement, what is the criteria, we have seen gain k is sufficient, so there is no need to design the lead compensator. Instead we can use a simple gain. But for the transient requirement, we need to have a lag compensator, and we have seen that it is not meeting the requirement, so we will design the lag compensator accordingly. So we will make here we there is no hard and fast rule as you have to follow in this way, but we will consider the zero location and then get the pole location. So here zero location, there is no hard and fast rule. We have started with considering ZC as zero point 0.1, and then we'll back calculate and then get. So we are assuming, say if it is not meeting, then we'll choose ZC less than zero point 0.1. And then all these things we have discussed thoroughly using the mathematical calculations as well as the MATLAB. Using MATLAB also we have done the same. And yeah, so then we have discussed about the lead lag compensation, which consists of both. So when we are trying to improve the transient response as well as the steady state error. So what are the step-by-step guidelines and how we are going to solve the problem? So first you have to design the lead compensation. So always try to achieve the transient response first, then the steady state error. So first we have designed the lead compensation, and for that we have to get the closed loop poles, and we have to follow the angle criteria and all the formula that we have gotten to design the lead compensation. And for lag compensation, we what is the criteria? We have to see whether gain is sufficient, else we have to use lag compensation and do the root locus. Yeah, so that's all about week 8. And this is I have not done mathematical hand calculations. Instead, I have used MATLAB. So that's why here majority of the things are missing. But I have written a MATLAB code for lead compensation, lag compensation, as well as lead lag compensation. And I have told what parameters you need to modify so that you will get the final gains, and it will also plot the transient response as well as you can see the steady state error. So that is a single click, and you have to make little tweaks here and there and understand how you are going to design that. So it is more iterative process rather than just solving by hand. So you have to use MATLAB, you have to solve by hand and then see whether it is meeting. If it is not, again do in the second iteration. So if you have any questions, you can ask until week 8. Also, this meeting is about to end. Once it ends, we'll come back and discuss week 9. So until then, if you have any questions, you can ask. Else, let this meeting
Sir,
end. We'll
in
come back.
exam, MATLAB questions will not come, no? Means
It may
by,
come
by
because they have given you MATLAB access, right?
exam also that will be provided.
Yes, yes, it may provide. Can you do one thing? Can you ask them just to be sure? Will not take any chances. You ask regarding calculator as well as MATLAB. Yeah, so whatever I was saying, let us not take any risk. Kindly drop a mail to NPTEL. In detail, ask them whether calculator will be provided. If it is provided, which type of calculator will be provided. Then you also ask them whether MATLAB related questions will come. If they come, will they provide access? All these questions you ask them because we are approaching the exam and you should prepare accordingly. Yeah, because I am not the TA of the course, because I don't have direct communication with the professor. I am a separate TA from the PMRF team that I am teaching the concepts as well as solving your problems. But how the exam paper is conducted or who creates the makes the question paper, I don't have any communication with them. Yeah. So this is week 9. Week 9, it is about lead and lag compensation or design using the frequency response, especially Bode plot. Previous week it was root locus. Now it is Bode plot. So week 8 is about root locus. Week 9 is using the Bode plot. So first we have discussed again the lead compensator. Then we have discussed regarding the lag compensator. So if we are having lead as well as lag, then what about the lead lag compensator? So all three compensators we have designed using the Bode plot. So we have started with the lead compensation, and we have seen what is lead compensation doing to the Bode plot, and by changing alpha, what is exactly changing. So I have also pasted it here. So depending upon the alpha, the magnitude at the higher frequency will increase, as well as the phase boost that it will provide also will increase. So depending upon our requirement, the alpha will vary. And these are the guidelines, step by step guidelines. Again, I'm not going through them in detail. So in this question they have given certain criteria. Based on that we got the gain, and then we have to see how much phase boost we need, at which frequency we need. Based on that we'll calculate phi m, then alpha as well as omega m. So there are step by step guidelines, and I have showed, because it's an iterative process, I will consider something it will not meet, so then I will try to improve it. So I have considered phi m to be 37, considering 5 degrees offset. And I have also explained why this will also come, because we are trying to increase the phase boost here, but this is not our gain crossover frequency. We are trying to have a gain crossover frequency here. So we there the phase boost will be slightly lesser. So we have considered 5 degrees as compensation, but we have seen it is not sufficient. So we might have to increase the offset and then do it in a iterative way. So 5% correction term, this is the case, and 8% correction term, this is the case. For 5%, I have seen it is not meeting. I've done 8%. Why again 8%? I've just started with 8%. Say if 8% is also not sufficient, then I'll go 10%. If it is also not sufficient, then I'll go to 12%. So in this way, we have to do in an iterative way. So that's why I have provided the MATLAB code, as well as I have put it here, so that I will, whenever I show these notes, it will be clear why we have done that. Then again, for the lag compensation, we have seen what impact it is creating, and lag compensation, what are the guidelines we have also listed down here. So here I have one question, and then we have seen whether we need phase lag or phase lead, and we have seen it needs phase lag. So how much phase lag is needed, where it is needed, and here also you need to have a correction term. So here we have started with correction term 10%, and we have seen whether it is able to meet or not. Say 10% correction term, we have seen it is not meeting, then we have met 12% correction term and it is meeting. So again, both that everywhere design is an iterative process. So you start with some point, and then make some assumptions, and then get design it, and then check whether it is meeting or not. If it is not meeting, then go back to where you have made some assumptions or considerations, try to modify them so that it will be meeting. Do the same thing, check. If it is not meeting, go back again, do the same. So it's in this iterative way we will check in the simulation. But if hardware is if hardware is also involved, simulation itself is not sufficient, because it will not fully capture hardware. So you'll do simulation, then test in the hardware, and if it is not meeting, then again run simulation. So it is always an iterative process. Learning is also such an iterative process, right? You learn week one, write the assignment, you see what mistakes you have made, go back, all again go through the lectures, learn in a better way, then try to solve the same problem. If you are still stuck, again come back. So in this way, every week you have done. Now we have finally reached the exam. So in the exam, for the exam, again now you are going back and then preparing everything, and then coming towards the exam and then giving the exam. So the objective is to get good grade in the exam. So for that, we are checking whether we have any faults in any concepts or any confusion. So if there is a confusion, we are going back, getting it clarified, and then we are coming to the exam. So the objective is to achieve good grade in the exam. So for that, we are doing an iterative learning. Then it's all about lead lag compensation. So here I have given one interesting example, and I have showed that lead compensation itself is not sufficient. So no matter how much phi m we are considering, it is not sufficient. So that's why lead itself is not sufficient. So then you have to design using lead as well as lag. So now the flexibility has doubled. It's not just lead, not just lag, but it is lead lag. So here I have so much freedom. Here I have so much freedom. So again, we have done step by step guidelines in how to do this iterative way, because now I have two variables that can vary. So there are infinite permutations and combinations, right? But I can't go abruptly. I have to follow some strict methodology or guidelines, and we have done this in this question. So we have started lead, then lag, and then again we have iterated to see whether we are able to meet the given requirements or not. So that's all about week 9, which was about design, and it again I feel that was interesting weekend. People were also interactive. If you have any doubts, you can always go through the lecture. So if you do not have any questions, I'll move to week 10.
Yes, sir.
Okay. So in week 10, it's about minimum and non-minimum phase systems. And if I'm not wrong, in week 10, I have also showed some RLC circuits experiments from our university towards then. So I'm not showing them, but it is already uploaded in YouTube, so you can go through them. So in non-minimum phase systems, we have identified what if there is RHP 0, what is the effect on the response, how to identify it from the Bode plot, what will be the Bode plot, and what is the criteria that it has to satisfy so that it is non-minimum, else it will be minimum phase system. And then we have seen the effect of RHP 0, how it is going to affect, and then if it is moved away from the imaginary axis, it is not having effect. So here we have considered multiple such case studies, and then I have given the MATLAB code, again you check. So based on this, we can come to conclusion that if it is having effect, where it is there. What if I don't want any effect? Then we have to make sure that the closed loop zeros or poles are moved away. So in that way, we'll design. And then we have considered one DC motor example, and then the transfer function. And I think Sir has considered Lego 3v3 DC motor. And for that to have the damping ratio 0.5, design a controller. So we have designed the controller, and then we have also drawn the Bode plot and saw. So there are three frequency regions, and in this frequency we have seen if the input is sine, what is the output, here what is the output, here is what is the output. And then I have also showed one interesting video for the sine response that we have taken in our lab during our experiments. And this is the response, critically damped, over damped, under damped, depending upon the criteria. So I have discussed about series RLC, and then I have showed the video on the series RLC. And if initially it is 0 and if we give sign, it will not directly go to sign, because there is one exponentially decaying term plus sinusoid term. Sinusoid term is steady state, exponentially decaying term is transient. So if it is stable, exponentially it will decay or it will grow. So week 10 was more of experimental design. So it was simple and straightforward. And I have also showed video, interesting video. So kindly go through the video, my YouTube video if you have missed those videos. So any doubt till week 10?
Sir, where to get that videos? Because I am joining first time to live
Okay,
session.
okay, okay. Just a minute. There are some important links that I have given in the chat. Let me go to the top of the chat, and then I'll give the link. So yeah, so I'm giving you three links. One is my YouTube channel, and one is the link to the Zoom meeting. And since this is the last meeting, it doesn't make any sense now, but I'm still sharing. One is the drive to access the notes. So all the notes that I have given, all the MATLAB codes that I have discussed, all are uploaded to this link. So I hope you have received my message. You save that message somewhere. You go through the YouTube videos that I have uploaded to my channel, and also access the notes through the drive. And if you have subscribed to my YouTube channel, you will get the notifications. And in each description of the particular video, I have also given the drive link, so you can also access the notes from there. But it is good to have the drive link handy so that you can access.
Okay, sir.
Okay. So in week 11, we have discussed about state space modeling, because we have told that the transfer function based design has some limitations which can be avoided using the state space based design. So in this week, it was more about state space modeling and not design. Design was in week 12. Here we have understood what is state space model, what are the matrices, what will be the order of the matrices, and how to get the state space model from a third order differential equation, fourth order differential equation, how to get these things. And then how to get the transfer function from state space, what is the formula, or how we can derive if you don't remember the formulas. All this we have discussed, and then we have solved a problem where we have converted state space to transfer function. And once we get the transfer function, we can comment on the stability based on the pole locations, and we have commented on the stability as well. And what if the system is not linear? Then you have to linearize it around an operate equilibrium point, and then get the model around that point. So in that case, how to calculate the equilibrium points, how to calculate the Jacobian matrix, we have solved using one problem. And if there are more number of equilibrium points, then you have to linearize around that equilibrium point, and the stability can be different for each of the equilibrium point. And here, if you see, this equilibrium point is stable, this is unstable. So depending upon the equilibrium point, the stability can change. So the system may be stable at some point, may be unstable at some point. If you ask me, sir, how is it possible? The standard example is the simple pendulum. At bottom, it is stable because any perturbation, it will come back. Whereas at the top, if I give any perturbation, it will move away from that operating point and reach the stable equilibrium point. So the bottom point is the stable equilibrium point, top point is the unstable equilibrium point. So there are two equilibrium points, one is unstable, the other one is stable. And then we have also discussed about the canonical forms from a given transfer function, how to get the controllable canonical form, and then how from controllable canonical, how to get the observable canonical form, and from there, how to get the diagonal form, how to get these matrices. We have discussed in thorough. And then one important aspect is the matrix exponential, how to get the matrix exponential using the inverse Laplace transform. And we have solved two problems based on that. And this is like the easiest way to solve this. So we have discussed this method in that week, and solved how to get the e to the power 80 matrix using the inverse Laplace transform. So that was all about week 11, more about state space modeling as well as transfer functions as well as this exponential matrix. If you have any questions, you can ask, else we'll move to week 12, which we have discussed yesterday itself. So I'll go a little bit fast.
Yes, sir, you can proceed.
Okay, okay. So in week 12, we have discussed about the design using the state space model. So we have discussed few concepts like controllability, what is the controllability test, how to check, and then we have solved three problems. First two being second order, and first problem we have seen it is controllable, and you have to calculate the rank of this matrix. And then again, I have given the MATLAB codes uploaded to the drive. You can access them from the drive. And in the second problem, we have seen that it is not controllable. And if it is not controllable, how to identify which is not controllable, and if it is not controllable, whether it is stable or not, that also we have checked and we found out it is unstable. And then in this case, we have third order system and we have seen that it is controllable. Then we have something called observability, which is like what states we can measure. So based on that, again there is an observability test. You have to check the rank of this matrix. We have solved couple of problems, starting with second order system, which is observable, and in the second case it is non-observable, not fully observable, only one is observable. And the third case, it is a third order system, which is fully observable. We have considered, but it may not be fully observable also, depending upon the matrix. Then we have discussed our pole placement method using state feedback control. So first we have discussed the theory, how to solve for these unknown values k to meet the desired closed loop pole criteria. So you have to get the A minus BK matrix. So A minus BK corresponding to the closed loop poles. So now K1 and K2, two equations. And then because it is second order, two equations, two unknowns. Had it been third order, it will be three equations, three unknowns. And then they'll give you three such closed loop poles. So I have also provided you one code where you enter the closed loop poles and it will give you the characteristic polynomial. So it will make our life simpler. And I do this to avoid calculation mistakes whenever I'm teaching. So I have used the MATLAB for that case. And we have solved for K1 and K2. And then I have also solved what if the desired closed loop pole locations are slightly different, what will be the characteristic equation. And then we have also discussed the full order observer. It is dependent on A minus LC. So to make sure the observer poles are at this location, what will be my L1 and L2 value? Two equations, two unknowns, and then we have solved for the L. So this is all about control engineering course and 12 sessions that we had throughout this entire course. I hope these videos are helpful. I have really enjoyed teaching you guys, because even I have done many things that I have not done in the past. Even I have tried to learn certain things to teach you, like MATLAB coding and some small concepts. And I have got to interact with all of you guys, and it was a really nice experience. I hope I have helped you. If you have any questions, you can ask, then we can discuss, else we can wind this session here.
No, sir.
Okay. So in such case, I'll end this session over here. Thank you. Thank you for making this session interactive, and whoever all have could not attend today and are watching this video, thank you for attending my lectures and making it interactive. I hope I was able to help you to understand the concept better and try to give some intuition in certain concepts. And I wish you all the best for your NSEM. Be thoroughly careful with the mathematical calculations. That's where most of you make mistakes. So first, understand all the concepts, go through the videos, solve problems, be confident about the calculations, solve as many number of problems as possible to avoid mathematical calculation mistake, and be confident, do well. But just check with the NPTEL team whether they'll provide calculator, as well as whether they'll provide MATLAB access, or if to be precise, whether they'll give questions related to MATLAB. If MATLAB access is given, you can make some calculations in MATLAB itself, and you can avoid the calculator. But yeah, it is always good to ask and cross verify rather than directly going to the exam. So be thorough with all the concepts, go through all the lecture videos as well as my videos, solve as many problems as possible, be confident, and I wish you all the best.
Sir, do you have any idea about exam pattern?
No, no, no. That's what. No, like I don't have any communication with the professor or the TA who is making the question paper. So we are a separate body who are there to teach you the concept and solve problems. But anything related to the assignments, like if there is any mistake in the assignment, or if you have any query regarding the question paper, I'm not the right person. You can directly contact the NPTEL team, or you can drop a question in the forum, and the corresponding TA will be replying to your email.
Okay, sir. Thank
Okay.
you.
Yeah, yeah. So yeah, thank you. I wish you all the best. I'll end the session here. Uh, all the best. Please go through all the lectures, and then yeah. Thank you for joining. Good night.